Again, welcome everybody. Today I'm going to talk about Bayesian Item Response Modeling in R with brms. And Stan, I'm trying to make this conceptually high level and then go a little bit into the syntactical details to fit item response model, IRT models in brms. So this talk is based on a paper of mine, which last year has been published in Journal of Statistical Software after, I think, being accepted for over a year and still being put on hold because it was part of a special issue, which was delayed a bit. So now it's there, it's officially published, but it was also there before in archive. So let's talk a little bit about general purpose IRT. So for item response modeling, we need a set of parameters, zeta I for item I, right? So every item has a bunch of parameters, zeta I. And for every person, we have a set of parameters, theta p. So for those of you who are not familiar with IRT modeling, who are just wondering what is happening here. So in item response modeling, what we do is like basically every person that attends some kind of test, let's say intelligence or creativity tests, they are going to answer, like in most cases, every item. That is basically, we have in the end a fully crossed matrix such that every person has provided response on every item. If that is some kind of ability tests, like intelligence, creativity or something, that could be part of IRT, or it could be some kind of personality tests. For example, if we were to measure something like extraversion, emotional stability, conscientiousness, something like that. And the goal of IRT would then be to measure both person and item parameters as closely as possible. For example, if we were to do some personal selection based on some intelligence test, we are really interested in getting those person parameters representing the person's ability, general intelligence, for example, as good and as precisely as possible. So in IRT, we are really concerned with measuring and modeling stuff as good as possible so that we have really valid estimates of what we later on are interested in, be it item or be it person parameters or both. Yeah? So every item has those item parameters, every person has the person parameters, and in usual cases, every person sees every item and the other way around. So a model for the responses YIP, so I for item, P for person, is very generally and holistically speaking, just like some kind of model given the item parameters of the item I and given the person parameters of the item P, of the person P. So in order to make sense, so in order to make sure that this model works at all in some reasonable ways, we need some kind of restrictions on the item and person parameters. Otherwise, we're ending up in situations that we would in classical statistics call non-identified, which basically tells us that we can't really estimate that model. Now, non-identified is not really a term that really makes sense in a lot of Bayesian statistics, since as long as we're specifying some like reasonable prior distributions, we always get a posterior distribution. But the problem remains that if the model is not identified in a classical frequentist sense, then chances are we won't get any sensible results with Bayesian models either, regardless of whether we get a posterior distribution or not. So we need some kind of restrictions, and like the specific restrictions don't matter here right now. We just have to keep in mind we have these kind of restrictions. So when we now do Bayesian IRT modeling, most of which stays the same. We're just replacing those kind of restrictions, some kind of restrictions with priors. So we're going to have some, for now, not specifically specified prior on the item parameters, and we have some not for now specifically specified priors on the person parameters. And that's really it. What means is that when we're doing Bayesian item response modeling as opposed to like just item response modeling, it's modeling-wise having a bunch of priors, and then estimation-wise having different estimation techniques, usually not optimization, but something like that can like estimate distributions, most likely MCMC, as for example in brms and STAN. So there's not really much to newly learn if you already know IRT and for some reason want to do Bayesian IRT, for example, because your model and your classical IRT models end up not converging, or there are some other problems. you want to try out Bayesian IRT, there's not much additional stuff you have to understand to get going there. And BRMS hopefully makes it easy in some ways, and I hope that this talk can help you with that. By the way, is actually this this Zoom pane, is it kind of in the way of the slides? Do you still see the full slide?
We still see the full slides.
Perfect,
yes.
because I don't, but that's good enough. Okay.
Well, we do.
So, okay, that's all I need. Okay, so let's extend that a little bit, make it a little bit more interesting, because I want to look at IRT models in the form of distributional regression. We will later see more like in terms of distributional multi-level models even. But I want to explain here what I mean by distributional regression. So first of all, we have to consider the data to be in long format. While before we had some kind of matrix of like items as rows of that matrix and persons on the columns of that matrix and the responses being in that matrix. When we're now actually wanting to do that in BRMS and a lot of other packages that represent IRT models as some kind of multi-level models, we need things in long format. That is, we need one long vector of responses, and then we have additional columns indicating the item number and the person number or person index to which that observation, that response belongs. So we're thinking of the responses to be in long format, and then we consider the pointwise, that is per response likelihood, in terms of distributional parameters psi1 to psi k. What I mean by that, so consider we had a normal likelihood. We just assume our responses would be normal. Then we would have two distributional parameters, mean and standard deviation, or mean and variance, depending on how we parameterize it. What we're usually doing in any kinds of regression models is, or in most like typical regression models, be them Bayesian or otherwise, that we only predict the mean or some other kind of location parameter of our likelihood, and then all the other parameters, for example, the residual standard deviation sigma in a normal model, would be assumed constant across observation. It would still be estimated, but assumed constant across observations, that is not predicted. What we're now doing in distributional regression is we allow not only the mean to potentially be predicted by some kind of regression model or by item or person parameters in IRT, but also all or subset of the other distributional parameters, for example, the residual standard deviation in the Gaussian model, or for example, if we had a skew normal model that had some additional skewness parameter, we could additionally model the skewness parameter as well, because perhaps items can vary in their skewness. Yeah? Or if you're more familiar with, for example, response time modeling, and I'm going to talk about that later in more detail. Sometimes in response times modeling, we would like to model response time with the exponentially modified Gaussian distribution. It's kind of a convenient choice, not necessarily principled, but convenient. And there we would also have something like mean, standard deviation, or some kind of variation measure, and some right skewness measure. So we could have like multiple distributional parameters, that all of which could be depending on item and person parameters in IRT. And that's what I'm trying to convey here in the second equation. So each or a subset of those distributional parameters can be connected to the item and person parameters by a response function fk, where k here indicates the distributional parameter. So distributional parameter k psi k is equal to some response function fk of the item and person parameters. When a response function is something that you're unfamiliar with, response functions are basically inverse link functions. So if we think of a log link, then the response function would be the inverse of it, that is exponential. Yeah? Or if we think of a logit link, then the inverse of it would be the inverse logit, or like logistic function. And that's typically what we have in generalized linear models. Just here with distributional models, we have this kind of regression model and the link function for each, or like at least multiple distributional parameters. Okay, let's take a look at binary IRT models of binary responses, which is perhaps the most common form of IRT models, where basically binary responses mean we have 0 or 1 responses. For example, When we just score an intelligence test and we score every item, whether it's correct, assign a 1, or incorrect, assign a 0. That's kind of just the typical case. And this situation, these responses, these binary responses, we would canonically model with a Bernoulli distribution of a single parameter psi that basically gives the success probability or the probability of giving the correct response. Now, of course, some items may be more difficult or easier than others, and some people may be like more able to solve these items than or to give the correct response than others. So quite naturally, we would like to relate this success or this correct answer probability psi to our person and item parameters. Yeah? And when we consider the Rasch model, which is kind of the most basic IRT model, if we will, then psi is like a function f, the response function that I'm going to explain in a second, of the sum of the corresponding item and person parameter, where here this person parameter theta p would be the ability, that is, the higher theta p, the greater the chance that this person answers that item correctly, and the zeta I would be an easiness parameter, that is, the higher zeta I, the easier the item is, that is, the more likely every kind of person will answer that item correctly. So for F, we could have different choices. Here, like in the canonical IRT Rasch model, we are choosing the logistic response function, i.e. the logit link, which is simply exp of that sum of theta p and zeta I divided by 1 plus that same term. And by doing this kind of response, we would ensure that our probability of answering that item correctly for a given person is always between 0 and 1. Okay, I want to pause here quickly and ask if there are any questions so far.
Wait, yes, there just came one question in the chat. Is there a specific reason for summing difficulty and ability?
What would be the alternative?
I guess that would be the add-on question. The convention is a subtraction.
Yes. So if we were to do subtraction, that is basically person minus item parameters, then the item parameters would be difficulty. That is, the higher the item parameter, the higher the difficulty. When we are adding the two together, then the item parameters are no longer difficulty, but easiness. That is, the higher the item parameter, the easier the item. I know the person who asked that knows that question. I'm just explaining it for the audience. So the reason I'm using here addition is that we are going to use a regression framework for that, where we just having one term plus another plus a third term plus a fourth, etc. So by having this easiness plus parameterization, it fits more easily in regression, but in any case, it's equivalent because the difficulty is just minus the easiness.
There is one more question here. Are the indices I and P really required? What if there are several I equals 1, 2, 3, and P?
For the same response, so I'm being a bit lazy with the indices here. Yeah. So I just want to indicate that whatever response we're talking about is for a specific item and for a specific person. I'm not using these indexes consistently across all the formulas here, just to try to ease the understanding of the general conceptual idea. But I'm not sure if that answers the question. Perhaps that the question would have to be clarified.
Yeah, that just came an add-on question. So should it be psi IP?
Yes, it should be. I was just lazy in adding that. Yes. Yeah.
good to see that other people are lazy as well.
Yeah, no. So here you just, the point is more like our predictions are always depending on a certain item and person, and all the quantities that follow from that also could have this IP index if we wanted to be strict. So this is just to be understood conceptually.
I think that was it for now.
Okay, perfect. So let's continue. So in this case of the Rasch model, be it Bayesian, estimated Bayesian or otherwise, we have one person parameter and we have one item parameter. So let's make the situation a little bit more complicated and go to the so-called 2PL or Birnbaum model, which is basically two parameter logistic model, PL for parameter logistic model. And what we're adding there is, in this case, a discrimination alpha I that basically tells us how steep the logistic curve is. So if the discrimination is higher, the steepness of the logistic curve would be higher as well. And we would say the item would be discriminating more strongly. So it would be more informative, if we will, about like ability differences. And if alpha I was smaller, then the item would be less informative. So if, for example, if you're aiming to like estimate person parameters quite precisely with fewer items, then probably highly discriminating items are the way to go, but also care need to be taken that there's some spread and difficulty of these discriminating items. We can go one step further and go for a 3PL model where we additionally have some guessing parameters. So for example, if we're in a forced choice experiment and there are 4 different options of which one is true, then even if the person doesn't know the right answer and they are still guessing the right answer with probability 25%. And this is something we could include in our model by basically multiplying our 2PL part with 1 minus this gamma I and adding gamma I, where gamma I then would be the guessing probability. So even if the person had no idea whatsoever what's going on, they would still have an expectation, a probability of answering this forced choice question correctly by 25%. So we could add on like more parameters, but I think the idea should be clear that as we are adding more item parameters or like person parameters, we could also add more. The problem becomes more and more complicated, and also the estimation becomes more complicated. And as models become more complicated, more nonlinear, we clearly see the 3PL model is quite nonlinear. Bayesian estimation tends to shine more because it is like more robust in terms of estimation performance, and we can make it additional robust by specifying prior distributions. Let's talk about priors. So we have lots of choices. I just want to conceptually differentiate between 2 options we are generally having. We can specify non-hierarchical priors and we can specify hierarchical priors. And this holds true for both item and person parameters. I'm just going to explain it for the item parameters here. Non-hierarchical prior in this case means that every item parameter zeta I gets its own independent prior with some kind of fixed hyperparameters. For example, in this Rasch model, we could say every of the difficulty or easiness parameters is a priori normally distributed with mean 0 and standard deviation 3, which for the logit scale would be a rather weakly informative prior, adding just a little bit prior knowledge about the understanding of the scale of the logistic model, but like nothing else. It would regularize the model, but make it a little bit more stable, but otherwise wouldn't add too much information. But the most important of the non-hierarchical part is the hyperparameters of the prior, this 0 and the 3s, mean 0, standard deviation 3 here, are fixed. Yeah? We just set them and that's it. Now compare that to the second option, which is a hierarchical prior. In which case, for example, our easiness parameter zeta I would be normally distributed again around 0, but now with a parameter sigma theta that would not be fixed by the user, but rather estimated by the model and gets its own hyper prior. So for example, we could say sigma zeta is half normally distributed with standard deviation 1 normal plus means it's a truncated normal and it's truncated at 0. So the normal plus pi with mean 0 and standard deviation 1, or with location parameter 1 and scale parameter, location parameter 0, scale parameter 1, would basically be a truncated normal that's just in the positive real line. The important part here, in the hierarchical formulation, all the easiness parameters of the different items are related to each other because they're sharing the same, in this case, single hyperparameter sigma theta. And by that means we are implying shrinkage as in all kinds of multi-level models. That is items that are specifically easy or specifically difficult get a little bit shrunken towards the mean. And I'm highlighting this here in terms of item parameters because if you're interested in IRT, you probably are familiar with the convention that item parameters get non-hierarchical priors, even if we don't call them non-hierarchical, or they rather don't get any priors at all, while the person parameter gets those hierarchical priors. And the logic that is usually applied here is that item parameters is just a fixed set of items. They're not coming from a population. We're just having some fixed item parameters, while the people are coming from a much bigger population, and we've just drawn a sample from that population, while the items are just like those items we're having, and there's no population they're coming from. And then that's used as an explanation of why we're having non-hierarchical priors on item parameters and hierarchical priors on person parameters. And what I'm trying to convey here is I don't really like this argumentation. So for me, whether I'm applying non-hierarchical or hierarchical priors is simply, do I want shrinkage or not? Do I want additional, this partial pooling, like shrinkage, depending on the other item or person parameters, or do I not want to do that? And my answer is usually I want that kind of shrinkage to make my model a little bit more robust. So my tendency would be to have both hierarchical priors on person and on item parameters. Although in BRMS you could do both to both, depending on what you would like. We could make that also more involved. So if we had multiple item parameters per item, for example, in the 3PL model, we had 3 item parameters like easiness, discrimination, and guessing parameter, and we could scale them appropriately with some link functions. Then we could model that hierarchically with a multivariate normal prior that not only had those standard deviations belonging to the specific parameters, but it would also have a correlation matrix here, omega, zeta, that would model the correlation. For example, we could think of a case where some items that are more difficult are also better discriminating or would have different guessing probabilities than other parameters. The exact notation here doesn't really matter. The point is hierarchical priors can also be applied if we have multiple parameters per item or multiple parameters per person. Okay, are there any questions about that so far?
Yes, there was a question that just came up. And the question is, to what extent is choice between hierarchical and non-hierarchical priors determined by the amount of data we have? If we have a lot of data, is shrinkage as critical?
That's a really good question. So that there are 2 different amounts of data. One is, for example, if we're thinking of item parameters here, how many items are we having? And the second amount of data is how many observations per item are we having? In this case, it would just be how many persons are we having if every person sees every item. So what we need to be careful with is if we are applying hierarchical priors, if we have just very few items, such that, for example, we had just 2 or 3 items, then having a hierarchical prior would be a little bit difficult because then that standard deviation parameter would just be estimated based on 2 or 3 items. Imagine estimating a standard deviation based on 3 observations. That's not going to end up being so well. In this case, perhaps we better go with a non-hierarchical version to avoid this additional hierarchical parameter. So that's one kind of amount of data. The other one would be the amount of persons. And yes, that's true. If we have a lot of persons, then probably the shrinkage won't matter too much. unless we are in cases where the responses on some items are really awkward. For example, very extreme, almost everybody answers them correctly or almost everybody answers them incorrectly, then things may become a little weird, and their hierarchical price can actually help stabilizing that. So it's not only the amount of data, also the amount of person, for example, in this case, but it's also the specific response pattern. So unless you have only very few items, probably hierarchical priors, at least I would prefer them, and in the quote unquote worst case, they would probably not be any different than the non-hierarchical ones.
Yeah, thank you. And there was another question, and it's, do shrinkage and regularization refer to the same concept?
Yes.
It's a simple answer. Thank you. That was all the questions.
Good. Okay, so after this kind of just general introduction, I want to show you a little bit how we can apply general purpose IRT models with BRMS and STAN. For those of you who don't know, STAN is a probabilistic programming language to fit open-ended Bayesian models. It's internally uses C++, so it's really, really efficient, really fast. And the STAN modeling language is accessible through R, through Python, Julia, command line, all the kinds of interfaces. It has its own language, which is a little bit something between C++ and R, but like very much easier to use than C++. And for those of you familiar with R, it's not too difficult. However, of course, setting up really complicated models involves a lot of work, a lot of expertise to set that up correctly, making it numerically stable, like having efficient parameterizations and so on and so forth. So there are like lots of packages that use STAN internally, but externally, for example, use an R interface. And one of these is my R package BRMS, which focuses on all kinds of regression model. Internally, it writes STAN code that is human readable, mostly, yet fast. But on the outside, all you have to do is basically specify a bunch of R code, mostly R formulas, and then you're good to go. So from now on, I'm going to use BRMS, but know that STAN handles things internally, and BRMS wouldn't be what it would be if STAN wouldn't be that great of a probabilistic programming language. Okay, so let's specify our IRT models in BRMS. We're going to start with a so-called family. While family basically means what kind of likelihood are we assuming. So we can use all sorts of like standard families that are available in R, such as Gaussian, Poisson, binomial, but we can also use that a little bit more general BRMS family interface, where we can have like access to a lot of more families. So in the BRMS family interface, we would specify the family, quote unquote, that is the likelihood, Gaussian, Bernoulli, binomial, Poisson, whatever you like, with the corresponding link function that applies to the main location, i.e. mean parameter. And if we had more distribution parameters that we wanted to predict, we could also specify more link functions that apply to these additional distribution parameters. For example, if we're looking at a binary model with a Bernoulli family, for example, to set up a Rasch model or something like that, all we have to do is say BRMS family, Bernoulli with a link, log it. If we had set up a distributional model that had, for example, both predictions of the mean and of the residual standard deviation sigma, then, for example, we would specify family Gaussian, link is identity, because we don't have like any relevant link function on the mean. We don't need to. We could, but we don't need to. And we would specify the log link on sigma, because standard deviation can only be positive, and by applying a log link or equivalently exponential response function, we are ensuring that our predicted sigma is always positive. If you don't specify the link functions, defaults are used. Here you're seeing the actual defaults just explicitly being spelled out. The formula. So here we're going to specify how exactly our responses are related to item and person parameters. If we just specify one formula, then it's just going to be applied to the mean parameter. So in the first formula, items have independent priors, persons have hierarchical priors. and our response would be y, and our item index would be item, and our person index would be person, then we would say y tilde 0 plus item plus this kind of random effects notation 1 pipe person. What does that mean? So first of all, everything before the tilde is the response, in this case called y. Then the 0 plus item ensures that if item is a factor, we're going to remove the intercept and instead have cell mean coding for the items. That is, for every item, we are going to have one fixed effect, like one coefficient per item. If we didn't use this 0 plus item, then we would have some kind of dummy coding, for example. This is general R formula syntax style, where just one item would be the reference and all the other item effects would be in reference to that reference item, which is a little bit awkward. So we're removing the intercept, ensuring cell mean coding for the items. Every item gets a coefficient and everybody's happy. So we are saying 0 plus item. And then we're using this LME4 random effects notation where things before the pipe, before this pipe symbol are the coefficients that are supposed to vary across the grouping factor behind after that pipe. So 1 here stands for intercept, and the person is the grouping variable. So we're having a specific intercept parameter for each person, which just means every person gets their own, for example, ability parameter. If we want to have both item and person parameters hierarchically, we're going to add the overall intercept 1 back again, and we're going to have this kind of random effects formulation, 1 pipe item, that is every item gets their own item parameter, but we're having internally this hierarchical prior, and the same with person. If we wanted to add a covariate, for example, the age of the participants, if there was a test that would be like who's like where the ability of the persons may depend on their age, we could add that covariate just as we could in any kind of other regression framework to have some kind of explanatory IRT models. It's just like multi-level regression with some additional predictors that could also vary, like as varying effects across item and person. We could make this now a little bit more complicated. So suppose we are having multiple distributional parameters, for example, one mean parameter, which is represent the first formula always. And then we had 2 additional distributional parameters, par 2 and par 3, each of which would be related to item and person parameters, to their own item and person parameters. Then we would specify 3 formulas, one for the main parameter, and then one for par 2, one for par 3. And we would combine that with the BF function, where BF stands for brms formula. It doesn't stand for base factor, so be aware of that. If you want to make that explicit, you could also write brms formula, which is just a little bit long. But BRMS supports also the second kind of interface for like multiple parameters, which is so-called nonlinear formula syntax. Remember, for example, in the binary IRT models, we didn't really have like a multiple distribution of parameters. We just had the success probability in some way, but we were relating that to multiple additional parameters, for example, discrimination and guessing. So for example, if our response y is some nonlinear function of, let's say, some covariate x and 2 nonlinear parameters, let's say discrimination and easiness or something, then we could specify some nonlinear function fun of that covariate x plus to the distribution of parameters. And then we would specify formulas, linear formulas for the 2 nonlinear parameters. And to make sure BRMS knows that this first formula with a y tilde fun is not treated to be like as a linear function, not parsed as usually are parsed as formulas, but literally treated literally as a nonlinear function, we're setting NL is equal to true, such that BRMS knows this is going to happen. Are there any? I'm going to add one more slide and I'm going to ask questions. So if we look at this again, then we have different item parameters per nonlinear distribution parameter, same with different person parameters, but they all are going to be estimated as independent. But as I said initially, it is very plausible that, for example, the easiness of items relates to their their discrimination, or for example, the ability of persons in a certain test, or like in a certain aspect, for example, mean response times could very well relate, i.e. is correlated with the person's ability in terms of, or person's property in terms of the variation of response times. There's a long literature on that showing basically that people who tend to have longer response times also have more variation in response times. So it may make sense to assume those different random effects of person or of items to be modeled as correlated. And in BRMS, this is realized across formulas by having two of these pipe symbols and then having a symbol in between them. For example, I for items and P for persons. It doesn't really matter what you put in there, as long as you put the same symbol in those terms that are supposed to be correlated. So if you want to correlate all person parameters with each other, two pipes and then a P in between, and all of them are going to be modeled as correlated, even across formulas, same with items. Okay, so before we're going to look at one application, are there any further questions?
Right now, there are no additional questions.
Good. Okay. Oh, there's a question, I think.
Well, a comment. Pretty cool stuff.
Perfect. Yes.
And now it's also a question coming. Are interactions expressed in the typical R formula way? Good
Yes,
question.
There are.
Yeah, that was it.
That was it. Okay. Good. Okay, so I know this was a little bit abstract in lots of ways. Let's make this a little bit more concrete by looking at one case study, which is the verbal aggression data set. Which is, I'm not sure if it's actually a real data set or if it's a simulated data set. Let's just pretend it's real. I don't know if it is, to be honest. And in this data set, we're going to analyze different kinds of verbal aggression and how they relate, for example, to the gender of people or to different kind of aspects of the items. So first of all, they are like people were answering certain items that asked if in a certain situation they would curse, for example, like or they would do some other actions that relate to verbal aggression. And there would be different modes. And the variable mode, for example, do they want to have that, show that verbal aggressive behavior, or would they actually show it in that case, right? So wanting is, of course, like one step further away from actually doing it than doing it. And there could be different situations, different kinds of verbal aggression. And the responses actually has 3 levels, which is no, I wouldn't show that verbal aggression behavior, or didn't want to do that, perhaps something between, and yes. So the recipe is this 3 outcomes, and the R2 column at the very end is just no or yes, whereas perhaps it's just coded as yes, which is just anything else than no would be coded as yes. And then we could be looking at, for example, how does gender relate to this verbal aggressive behavior or wish to do that, or how does kind of the general trait anger, like here listed in the anger column, relate to these features. So there are like lots of things in terms of item and person covariates going on that we could look at. So now I have to actually move this bar that you don't see so that I see what I'm actually writing here. So let's focus on the binary response case R2 in BRMS via ordinal models. We could also model the 3 responses, but we just focus on the 2 responses case here. And if we're just fitting a 1PL that is a Rasch model with hierarchical price and item and person parameters, where item is indicated by this item column and ID is the person column, then we would specify our Rasch model with hierarchical price and item and ID. And by the syntax, we automatically have the hierarchical prior. We wouldn't need to specify explicitly the prior for that. But what we could specify if we wanted to is the specific prior for the standard deviation of those random effects of ID and of person and of item. And here, for example, we would specify that standard deviation parameters as being half normally distributed 0, 3. This half is not specified here, or this truncation is not specified here, but it happens implicitly behind the scenes. So BRMS makes sure rather that we're having always the right boundaries. Standard deviation can only be positive. BRMS makes sure that's the case, and Stan translate this normal 0, 3 prior to truncated normal 0, 3 prior truncated at 0. And then we would put everything together using the BRM call. So we would specify our formula, our data set, our prior, and our family, which in this case would be Bernoulli with our logit link. Then we could, for example, run the plot method. We could see the marginal density of the parameters. B-intercept is the overall intercept here, and SD-ID intercept is the standard deviation across the person parameters of the intercept. Here we just have intercept, so it's just the person parameters. The SD item intercept is the standard deviation across items. And if we look at the right-hand side, we see that we have fitted 4 MC-MC chains. So we're using Bayesian estimation to fit the posterior distribution. I'm not going to talk about that in detail in the interest of time here, but we see things have been mixing quite well. So our Bayesian model has been able to obtain, at least for those 3 parameters, a quite trustworthy posterior distribution that we can use for further inference. Now we could, for example, look at the item parameters. So on the x-axis, we see the estimate of the item parameter. On the y-axis, we see the item number. We have the easiness parameterization. So we see that kind of items with a lower number that were initially, like at the start of the test, are rather easy, while to the end, we're getting more difficult items that, like in this case, difficult would mean fewer people would agree to that item. Which is basically the reason I think the first items are more like, do I want to show verbal aggressive behavior? While the later items are more like, would I actually do that? And this apparently is something that fewer people do actually show verbal aggressive behavior than people who want to show that, which I think all of us can relate to, I guess. So now let's get a little bit crazy and fit a 2PL model. So 2PL model, we have this, we have the item easiness, we have the item discrimination, and we have still the personability. So we are separating that model in 2 parts. First of all, this what I'm calling eta, which simply has the item easiness and the personability or person parameter. And then we're having the discrimination. And the discrimination is something that usually can only be positive. So we want to ensure that it's positive. And the way we do that is we are specifying our item discriminations on the log scale. And then after exponentiating it, they're going to only be positive. That is, we're having our linear formula on some kind of scale where we can assume things to be linear. And then we're transforming them, for example, here with an exponential transform, such that they adhere to the correct restrictions we want to apply. For example, discriminations can only be positive. So that's using the nonlinear formula syntax. So R2 is non-linear related to exp of the nonlinear parameter log alpha times the nonlinear parameter eta. And then we're plugging in our linear parameter or linear formulas for eta and log alpha. Prior specification becomes a bit more involved. We didn't have to specify any priors. BRMS would take care of them in terms of default priors. But yeah, I mean, that doesn't mean they're always sensible. So I would always recommend that you specify default priors, that you specify your own priors and don't necessarily rely on the default priors. And I want to bring your attention to the 3rd line of the prior specification, which is this constant 1 of the SD class of the standard deviation of group ID, which basically means here we are fixing the standard deviation of our person parameters to 1, that is this constant 1. And the reason why we're doing that is if we didn't do so, we would have a non-identification problem, because the average discrimination and the standard deviation of the person parameters are not jointly identified. We could get away with them like without specifying this constant, just by having proper priors on both average discrimination and on the standard deviation of the person parameters. But still the scale wouldn't tell us much. And like, even if we would get results the scale would just be fully determined based on our priors, which is not necessarily what we want. So what we can do is we can directly solve or resolve our identification problem by fixing the standard deviation to one of the person parameters, which is something that is also commonly done generally in IRT models. Okay, so if we were, for example, to compare those two models, one with discrimination, the 2PL model, and one without discrimination, the 1PL model, and we would do model comparison, for example, with approximately Wiener cross-validation, we would see that the 2PL model fits a little bit better, although not so convincingly so. So very quickly, when we are running this comparison via Wiener cross-validation, the model that is shown in the first row is the best model. All models are going to be compared to the best model, so the best model against the best has 0 difference. And then we have an ordering of all following models. In this case, we are just 2, and the 1PL model is a little bit worse, but the uncertainty in that difference is also quite great, so we don't really have good argumentation for using one or the other models. So let's stick to the 1PL model for now and do some sort of explanatory IRT by adding a lot of predictors. For example, the B type, which I forgot what it actually meant, is basically whether we're going to curse or scold, so different kinds of verbal aggression we would like to do. Situation is the situation that is described in the item. Mode is whether people actually want to show that verbal aggressive behavior or do it. Anger is kind of some kind of trait anger, how angry people are in general, and gender is the self-assigned gender of those people. Now we could predict all of that in an explanatory IRT model, and we could even say we assume that items have differential item functioning, for example, across gender. So some items may be easier or more difficult for the different genders. Or we could say that people are differing in how they react to the different mode that is want or actually do showing the verbal aggressive behavior. And we can, for example, do that like that. So 0 plus gender would mean we would have one item parameter, and we would have like 2 item parameters per item, one for assigned male and one for like self-assigned female, and for mode do or actually want or actually do show the verbal aggressive behavior across persons. And again, we can run that model. And when we're looking at the conditional effects or conditional predictions of the interaction of mode and gender, we would actually see that both genders, and at least in this example, there were apparently no non-binary people present, so we just have 2 genders here, show the same or roughly the same kind of probability of wanting to show verbal aggressive behavior. But then when it comes to actually doing those verbal aggressive behavior, females would rate their probability of doing that much less, roughly around 70%, while males are way above 80%. So we're seeing that in terms of actually doing the verbal aggressive behavior, at least in this data set, males have higher probability according to their self-reports on these items. Okay, are there any more questions?
Currently, there are no, well, I shouldn't start talking too early. Now a question came. So the question is, why is the error bar larger for female, even if more female were present in the data set?
So I just trust you that there are more females in that data set, which I don't know out of my mind. But, so suppose that's the case. The reason is that we're having an upper boundary at 1, right? So there are 2 reasons. First of all, as you see at the variance of like the Bernoulli distribution, the variance is the success probability, or like probability of saying yes, times 1 minus that probability, which is highest when we are like having a probability of 0.5 and lower as we go to the more extreme. So that could contribute here to that uncertainty. And the other could simply be that there is less variation across males than there is across females. And as a result, the average effect that we're seeing here, like the average, quote unquote, let's treat it like that for a second. For the average across females and average across males, there's the average across females is more certain because there's less variation across female participants than there is across males. Both mechanisms could apply here. I suspect it's probably the second. So what we have to do, we would have to check whether the variation in these effects is greater in females than it is in males, and perhaps that could explain that behavior.
Yeah, thank you. And that was it for now.
Okay, so there's another example where we're actually analyzing response times. In the interest of time, I'm going to only go quickly over that, just to give you an idea what we could do. So for example, here in this rotation data set, we're interested in modeling the ability for people to mentally rotate an object. So we see two objects, one is rotated against the other on the screen, and we have to mentally rotate it back in order to determine whether those two objects we see on the screen is in fact the same or not. And this task is more difficult the stronger the rotation is of one object against another. So we have 3 rotation degrees, 150, 150 degrees. And what we are seeing here is the time in seconds that people take in order to respond. And resp here is coded 1 if they're responding correctly. That is, if they're correctly saying it's the same object, just rotated, if they're correctly saying it's not the same object. And so resp 1 would mean people have better ability in doing that task. And if they do it with lower response times, then of course the better. And we could analyze that data set, for example, with Wiener drift diffusion models, which is kind of cognitive models that are quite involved, but could also be used in IRT. So here we would have 4 distribution parameters. The most important is here denoted as V. That's the drift rate. That is whether we are drifting in the positive direction, which in this case, in our example, would be towards a correct response, or drifting towards a negative response. Whereas V would be positive, would be drifting towards the correct response. We would have the boundary factor A, which would basically tell us how far kind of the mental boundary is of people until or threshold is until they decide to make a decision. So they're accumulating evidence, they're mentally rotating, and at some point say, okay, I think it's the same object or not. And then at some threshold, they're saying they're making the decision, and this threshold may vary across people. Some people may be more cautious, where their boundary separation would be bigger than other people. And then the third parameter that is here of interest is the so-called non-decision time, that is related to all the time involved that is not about the mental process that we care about, but about other things such as actually the visual process of seeing the object, or the motor response of initiating the response, which is not our cognitive process that we are interested here. So all of them would go into non-decision time, and what we're interested here that would actually have a drift would be the mental process that decides what we are choosing. So whether we're choosing it's the same or it's the other object, or here whether it's then our correct choice or the incorrect choice. So very quickly, we would model the drift rate, which is the main parameter in that model, by both person and item parameters. And we could also model the boundary separation, BS, and the non-decision time as varying across persons and items, because people may be more or less cautious, having different boundary separation, or could be more or less quick in non-decision relevant tasks, which would affect the non-decision time. And similar items would also induce like different drift rates, different boundary separations, and different non-decision times, depending on how the items look exactly. So we can model that with this distribution framework. And then we could look at the results, where mu here is the drift rate. So we see that for rotational degrees of 50 degrees as compared to 100 or 150, people have higher drift rate. That is, they are drifting quicker to the response, which is 1, which in this case indicates a correct response, which basically indicates that rotation of 50 degrees is easier than 100 or 150 degrees, while 100 or 150 degrees doesn't really make a difference. In terms of boundary separation, we don't really see that there's any effect of the degree of rotation. So that doesn't really matter in that case. But we see the non-decision time is actually way quicker for the lower rotation. So apparently there are aspects of that task that are, according to the model, not related to the kind of the decision process itself, that make those rotation by 50 degrees in some sense easier. Whether that's actually cognitive modeling wise valid or not, or rather an artifact of the data, I cannot fully tell. Okay, so to summarize, and then you can also ask questions about the last example. So when you're interested in learning more about BRMS and STAN, you can check out the initial help page of BRMS. You could look at the set of vignettes that BRMS has. When you've fitted models and want to learn what kind of post-processing you want to do, you can use the methods function with the class BRMS fit. BRMS has a website that you can use. Stan has a website too. And what I should have added here, we have a forum, which is the Stan Discourse Forum. So if you're Googling Stan Discourse Forum, there you can ask BRMS and Stan related questions. Please don't ask BRMS related questions as BRMS issues, because they don't reach such a wide audience as in the Stan forums, and also there are way fewer people to answer your questions. So please ask questions at the Stan Discourse forums. If you like, you can also contact me via email or tag me on Twitter. If you have specific BRMS related questions, again, I would like to ask you to ask them in the Stan Discourse forums. There are a lot of people active and a lot of people very willing and able to answer your questions. Thank you so much for being here, and I'm now happy to now answer all the further questions you may be having.